binomial. We now have two hard-won identities, and so we should hold them. A basic binomial identity involving k times Bn of k, and one we've discovered with just a little bit of algebraic effort, an identity involving k squared times Bn of k. The first of those will be immediately useful, the second very shortly. So let's write down the expression for the expectation of the accumulated number of successes, E of Sn, also in the common language called mu, and given by a weighted sum of binomial probabilities. To the term k times Bn of k, we immediately replace it by our basic binomial identity. Since n times p does not depend upon k, it can be pulled out of the sum, and now we've got a sum of binomial probabilities involving a tacit experiment where a coin has been tossed n-1 times, and we're summing over all k. As we sum over all k, then we sum over all possibilities for successes in those n-1 tosses, from 0 successes all the way up to n-1 successes. And the normalization of probability measure tells us that this sum must be exactly 1. And so the sum just vanishes quietly like the snows of yesteryear. And what remains is simply np times 1, or of course just n times p. One could hardly ask for a simpler, cleaner, more intuitive solution to the problem. The expectation of a binomial distribution corresponding to n tosses of a coin whose success probability is p is exactly n times p. The expected value, the probabilistic center of mass, coincides with the maximum probability. The picture here, this at some level might seem obvious, but not at all so really, because one could imagine a setting where one had a mastiff, let's say, where one has a sharp peak and then a long fallout. If you had something like that, then yes, you do have a unimodal character, but most of the mass is on the other side of the peak, and therefore the center of mass will be very far from the maximum value. The fact that this does not happen for the binomial is important, in fact hugely important. What our calculation tells us for the expected value is that not only is the maximum probability around n times p, but this is a true center in that the probabilities, the masses, are distributed fairly evenly around the center. Not exactly equally, but roughly evenly, in such a way that the center of mass coincides exactly with the point where the probability is largest. We have further evidence now that our estimation procedure actually is doing something very well and very correctly. The maximum likelihood estimate of an unknown p turns out to be S sub n divided by n. And now we've got two more pieces of evidence telling us that this is actually very reasonable, very intuitive, very proper. Sn of n is not just the maximum likelihood estimate of p, it is the place where you have the largest binomial probability, and it is also the place where the center of mass of the entire distribution lies.